Question 1, Part A. Factorise 9x squared minus 16. It's important to recognise that the expression 9x squared minus 16 is a difference of two squares. Now recall that a squared minus b squared factorises to a plus b in brackets times a minus b in brackets. So if we let a squared equal 9x squared, so that's the first term of this expression, taking the square root of both sides, we get a is equal to 3x. Letting b squared equal 16, taking the square root of 16, we get b is equal to 4. Therefore, 9x squared minus 16 factorises to 3x plus 4 in brackets times 3x minus 4 in brackets. Question 1, Part B. Find the value of 19 to the power of negative 0.5 to 2 decimal places. It's generally good practice with any decimal rounding question to write down the full decimal answer that appears on your calculator screen and then do the rounding as a separate step, rather than rounding directly off the calculator screen. Now in this particular question, there are 2 marks allocated. 1 mark for correct evaluation and then another mark for the correct rounding. Now using the power button on the calculator, now on this particular model, that's this button here, 19 to the power of negative 0.5 is 0.229415739. And I've written the full decimal answer here. Now we need to round this decimal answer to 2 decimal places. So the first decimal place after the decimal point is this 2 here. The second decimal place is this 2 here. Now look to the third decimal place. If it's 5 or more, raise the score, as the saying goes. In other words, this 2 here needs to be rounded up to a 3 because the value after the 2, directly after, is 5 or more. So 19 to the power of negative 0.5 is equal to 0.23, correct to 2 decimal places. Question 1, Part C. Convert 3 pi over 5 radians to degrees. Recall that pi radians is equivalent to 180 degrees and vice versa. Thinking algebraically, pi is a constant that represents 180 degrees. Hence, 3 pi over 5 radians can be written as 3 over 5 times pi, or 3/5 of pi, replacing pi with 180 degrees. 3/5 of 180 degrees is 108 degrees. Question 1, Part D. Simplify x over 3 plus 3x minus 1 over 2. We are adding 2 fractions with different denominators. So the first step is to express both fractions, x over 3 and 3x minus 1 over 2, with a common denominator. A simple way to do that is to take the first fraction, multiply the numerator and the denominator by the denominator of the second fraction. So x over 3 times 2 over 2. Repeat the same thing, but with the second fraction. Multiply the numerator and the denominator by the denominator of the first fraction. So 3x minus 1 over 2 times 3 over 3. Now x over 3 times 2 over 2 is 2x over 6, so that's an equivalent fraction to x over 3. And 3x minus 1 over 2 times 3 over 3 is equal to 9x minus 3 over 6. We've now expressed both original fractions into their equivalent forms with a common denominator. So 2x over 6 plus 9x minus 3 over 6, those 2 fractions can now be combined together by combining the numerators. So combining the numerators, we have 2x plus 9x minus 3. So 2x plus 9x is 11x. Then we have the minus 3. There's no like term there, so we leave that alone. So the numerator is 11x minus 3 and the denominator is 6. Question 1, Part E. Find a primitive function of 2x plus 11. A primitive function is found by integration or anti-differentiation, and that's in contrast to finding a gradient function or a derivative, which we find by differentiation. So think of primitives and derivatives as opposites of each other. Hence, the integral of 2x plus 11 dx is equal to 2x squared over 2 plus 11x plus the constant of integration c. Now 2x squared over 2 simplifies to x squared. So the integral of 2x plus 11 dx is equal to x squared plus 11x plus c. Note, time permitting, check your answer by differentiation. In other words, differentiate x squared plus 11x plus c and check to see that we get the integrand 2x plus 11, which of course we do. Question 1, Part F. Express 0.23 recurring as a fraction. There are two methods we can use to express a recurring decimal in fraction form. In the first method, we can use fundamental algebraic techniques, and I'll go through that shortly. In the second method, we can consider the limiting sum of a geometric series. Let's consider the algebraic techniques method. Let x equal 0.23 recurring. Multiplying both sides of this equation by 100, effectively shifting the decimal point over to the right by 2 places, we get 100x equals 23.23 recurring. Now, if you recall, a recurring decimal is a decimal that just repeats itself. So 0.23 recurring is 0.232323 and so on. So moving the decimal point over 2 places does not change the recurring component of this value. Now, if we take this equation here, 100x equals 23.23 recurring, and subtract from this equation the first equation here, x equals 0.23 recurring, we get this. We get 100x minus x equals 23.23 recurring minus 0.23 recurring. Now the recurring components will cancel, and 100x minus x gives us 99x. So 99x equals 23. Dividing both sides of this equation by 99 to isolate the x, we get x is equal to 23 over 99, which is the fraction equivalent of 0.23 recurring. In the second method, we will consider the limiting sum of a geometric series to write 0.23 recurring as a fraction. Firstly, express 0.23 recurring as a geometric series, and that can be written as 0.23 plus 0.0023 plus 0.000023 and so on. Now the first term of this geometric series is 0.23 and the common ratio is 1 over 100 or 0.01. Using the limiting sum formula, S infinity is equal to A over 1 minus R, where A is the first term and R is the common ratio. We get S infinity is equal to 0.23 over 1 minus 0.01. And that equals 0.23 over 0.99, multiplying numerator and denominator by 100, so we have integers in both numerator and denominator, we get 23 over 99. Question 1, Part G. Solve 5 minus 3x less than 7. We can solve this inequality in a way that preserves the direction of the inequality symbol up until the very end. In this case, we have a less than symbol here. So this negative 3x can be moved over to the other side so it becomes positive. So the inequality becomes 5 less than 3x plus 7. The positive 7 on the right-hand side can be moved over to the left-hand side so it becomes negative 7. So the inequality becomes 5 minus 7 less than 3x, and 5 minus 7 simplifies to negative 2. So the inequality becomes negative 2 less than 3x. Dividing both sides of the inequality by 3 to isolate x, we get negative 2 over 3 less than x. Reading it backwards, we have x is greater than negative 2 over 3. So when we express the solution to an inequality, we have the variable on the left-hand side. So therefore, x is greater than negative 2 over 3. And here is the solution expressed in graphical form. Notice the open circle above negative 2 over 3 with the arrow pointing to the right-hand side. Question 2. The line L cuts the x-axis at L, negative 4, 0, and the y-axis at M, 0, 3 as shown. N is a point on the line L, and P is the point 0, 8. Copy the diagram into your writing booklet. Part A. Find the equation of the line L. To find the equation of a line, we need to find its gradient or slope, and we also need a point on that line. Now, the gradient of line L is 3 over 4. And if we consider triangle OLM, that's this triangle here, the gradient is found by change in y divided by the change in x, that is rise over run. Now, it's convenient that we have the y-intercept and the x-intercept. So the change in y is 3, the change in x from left to right is 4, which is why the gradient of line L is 3 over 4. And the y-intercept of line L is 3. So that makes it convenient to express the equation of line L in gradient-intercept form. That is in the form y equals mx plus c. So the equation of line L is y equals 3 over 4 times x plus 3. Alternatively, we can write the x in the numerator. So we can write it as y equals 3x over 4 plus 3. Part B. Show that the point 16, 15 lies on the line L. Given that the equation of line L is y equals 3x over 4 plus 3, or 3 times x divided by 4 plus 3, which we found in part A, we need to show that the left-hand side equals the right-hand side in this equation when x equals 16 and y equals 15. Now from the right-hand side, substituting x equals 16 for x, we have 3 times 16 in brackets divided by 4 plus 3, which evaluates to 15, which equals the left-hand side. Therefore, the point 16, 15 lies on the line L. Part C. By considering the lengths of ML and MP, show that triangle LMP is isosceles. Referring to the diagram, the points M and P lie on the y-axis. So the length of interval MP is the difference between 8 and 3, which is 5. Now the length of ML is found by considering the right-angled triangle OLM, since the y-axis and the x-axis are at right angles to each other. Now the interval LM is the hypotenuse of this right-angled triangle, and the length of the two short sides are 3 and 4. So using Pythagoras' theorem, the length ML is equal to the square root of 3 squared plus 4 squared, which equals 5 units. So the length of MP is 5 units, the length of ML is 5 units, MP equals ML, therefore triangle LMP is isosceles. Part D. Calculate the gradient of the line PL. Considering right-angled triangle OPL, we want the gradient of the hypotenuse PL. Now, the change in y, or the rise, is the difference between the origin and point P, and that's 8 units, and the change in x, or the run, is the difference between point L and the origin, which is 4 units. So using the formula, gradient equals rise over run, or change in y divided by the change in x, we have 8 over 4, which equals 2. Part E. M is the midpoint of the interval Ln. Find the coordinates of the point N. it is given that m is the midpoint of the interval Ln. This means the horizontal distance from L to m is equal to the horizontal distance from m to n, and the vertical distance from L to m is equal to the vertical distance from m to n. So horizontally, the distance from L to m is 4 units. That's the difference between -4 and 0. Which means horizontally, the distance from m to n is also 4 units. Now the x-coordinate of point m is 0. Adding 4 to 0, we get 4, so the x-coordinate of point n is 4. Now in the vertical direction, the vertical distance from point L to point m is 3 units, which means the vertical distance from point m to point n is also 3 units. So adding 3 to 3, we get 6, so the y-coordinate of point n is 6. And I've written the explanation here. The horizontal distance from L to m is 4 units, hence the horizontal distance from m to n is also 4 units. So the x-coordinate of n is 4. The vertical distance from L to m is 3 units, hence the vertical distance from m to n is also 3 units. So the y-coordinate of n is 6. Therefore, n has coordinates 4, 6. Part F. Show that angle NPL is a right angle. Two lines or intervals form a right angle if the product of their gradients is -1. In other words, gradient m1 times gradient m2 equals -1. It also works in reverse. If two lines form a right angle, then the product of their gradients is -1. Now in this case, the gradient of PL is 2, and we found that in part D. But we need to find the gradient of Pn. Now we can use the 2-point formula, and in part E we found the coordinates of point N, which has coordinates 4, 6. So using the 2-point formula, the gradient of Pn is equal to y2 minus y1 in brackets divided by x2 minus x1 in brackets. In other words, change in y divided by change in x, or rise over run. And that equals to 6 minus 8 in brackets divided by 4 minus 0 in brackets, which evaluates to -1/2. So multiplying the two gradients together, 2 times -1/2 is equal to -1. Therefore, angle NPL is a right angle. Part G. Find the equation of the circle that passes through the points N, P and L. The circle is centered on point M with coordinates 0, 3 with radius 5 units, since ML equals MN, which equals MP, which equals 5 units. In other words, ML, MN and MP are the radii of this circle. So the equation of this circle is x squared plus y minus 3 in brackets squared is equal to 5 squared. Expanding the brackets, we get x squared plus y squared minus 6y plus 9 equals 25. And moving everything over to the left-hand side, so we have 0 on the right-hand side, the equation is x squared plus y squared minus 6y minus 16 equals 0. Question 3, Part A, Part 1. Differentiate 2 times x to the power of -3. d dx, or the derivative of 2 times x to the power of -3, can be written as 2 times d dx of x to the power of -3. Now, the 2 is a multiplying constant, so that can be placed in front of the d dx operator. So differentiating x to the power of -3, we take the old index, or the current index, we place it at the front of the x, and then we reduce the power by 1. So reducing the -3 by 1, the new index becomes -4. So the derivative is 2 times -3 times x to the power of -4, which simplifies to -6 times x to the power of -4. Part 2. Differentiate 4 times e to the power of 2x. The 4 is a multiplying constant, so it can be placed in front of the ddx operator. So the derivative of 4 times e to the power of 2x can be written as 4 times the derivative of e to the power of 2x. And that's equal to 4 times e to the power of 2x multiplied by the derivative of the index 2x, which is 2. So 4 times e to the power of 2x times 2 simplifies to 8 times e to the power of 2x. Part 3. Differentiate x times log base e of x. The expression x times log base e of x involves a product of two functions of x. So the product rule will need to be used to find the first derivative. So ddx of x times log base e of x using the product rule is ddx of x times log base e of x plus x times ddx of log base e of x. So if y is equal to x times log base e of x, let u equal x and v equal log base e of x, then y dash is equal to u dash v plus uv dash. So that's another way to state the product rule. In this case, ddx of x, so the derivative of x is 1 times log base e of x plus x times the derivative of log base e of x, which is 1 over x. And x times 1 over x simplifies to 1, and 1 times log base e of x is log base e of x. So the derivative is log base e of x plus 1, or it can be written using the ln notation, ln of x plus 1. Question 3, Part B. A horizontal bridge is built between points A and B. The bridge is supported by cables SP and SR, which are attached to the top of a vertical pylon ST. The section of the pylon, SQ, above the bridge is 8 meters long and angle SRQ equals 52 degrees. The distance AQ is 22 meters and P is the midpoint of AQ. Part 1. Find the length of the cable SR. Consider right-angled triangle SQR. Now the size of the reference angle, angle SRQ, is 52 degrees and the length of side SQ is 8 meters. Now the question is asking us to find the length of cable SR, which represents the hypotenuse of this right-angled triangle. So we have the length of the opposite side, that's the side opposite the reference angle. We want to find the length of the hypotenuse, so we need to use the sine ratio in order to do so. And we can form this equation. Opposite over hypotenuse, so 8 over SR is equal to sine 52 degrees over 1. Now there's a reason why I wrote the right-hand side this way, sine 52 degrees over a denominator of 1. And the reason is we want SR to be in the numerator, not the denominator of the fraction on the left-hand side. So taking the reciprocal of both sides of this equation, we get SR over 8 is equal to 1 over sine 52 degrees. Now we can isolate SR. Now SR is being divided by 8. The 8 can move over to the other side by multiplication. So we write it in the numerator of the fraction on the right-hand side, since 1 times 8 is 8. So we get SR is equal to 8 over sine 52 degrees, which evaluates to 10.152145 and so on. I'm going to express the answer correct to 2 decimal places. Therefore, cable SR is 10.15 meters, correct to 2 decimal places. Part 2. Find the size of angle SPQ to the nearest degree. Consider right-angled triangle SPQ. Now the question is asking us to find the size of angle SPQ. So we need two known sides in this triangle. We know side SQ, that's 8 meters, that's the side opposite the reference angle. We need one other side, either the hypotenuse, SP, or the adjacent side, PQ. Now it's given that AQ is 22 meters and point P is the midpoint of AQ. So it's easy enough to find the length of PQ, which will be half of AQ, half of 22, which is 11. So we have the opposite side, we have the adjacent side, so that's 8 and 11. we need to use the tan ratio in order to find the size of angle SPQ, and we can form this equation. Tan of angle SPQ is equal to opposite over adjacent, so that's 8 over 11. We need to isolate angle SPQ, in other words, make angle SPQ the subject, and we do that by taking the inverse tan of 8 over 11. So angle SPQ is equal to inverse tan of 8 over 11, and that evaluates to 36.02737 and so on degrees. Therefore, angle SPQ is equal to 36 degrees, correct to the nearest degree. Question 3, Part C, Part 1. Find the integral of e to the power of 3x dx. Let's look at this from the point of view of differentiation. If we differentiate e to the power of 3x, we get 3 times e to the power of 3x. If we divide both sides of this equation by 3 to isolate e to the power of 3x, we get 1 over 3 times the derivative of e to the power of 3x equals e to the power of 3x. Now this 1 over 3 is a multiplying constant, and I can bring that back inside the derivative. So 1 over 3 times d dx of e to the power of 3x can be written as d dx of e to the power of 3x over 3, and that equals e to the power of 3x. So working backwards, or in reverse, if we integrate e to the power of 3x, we get back to what we started with, which is e to the power of 3x over 3. Therefore, the integral of e to the power of 3x dx is equal to e to the power of 3x over 3 plus the constant of integration c. Part 2. Find the integral of sine 2x dx from x equals 0 to x equals pi over 2. The integral of sine 2x with respect to x is negative cos 2x divided by the derivative of 2x, so divided by 2. And that's from x equals 0 to x equals pi over 2. Now we can clean this expression up a little bit. The divide by 2, we can write it as 1 over 2 outside the square brackets, and we can also take the negative outside as well. So the primitive function is negative 1 over 2 times cos 2x from x equals 0 to x equals pi over 2. Applying the limits of integration, we get negative 1 over 2 times open bracket cos pi minus cos 0 close bracket. Now cos pi is negative 1 and cos 0 is 1. So we get negative 1 over 2 times open bracket negative 1 minus 1 close bracket. Now negative 1 minus 1 is negative 2, and negative 2 times negative 1 over 2 is 1. Question 4, Part A. A simple instrument has many strings, attached as shown in the diagram. The difference between the lengths of adjacent strings is a constant, so that the length of the strings are the terms of an arithmetic series. The shortest string is 30 centimeters long and the longest string is 50 centimeters. The sum of the lengths of all the strings is 1,240 centimeters. Part 1. Find the number of strings. Since the first term, the last term, and the total sum of string lengths are known, use the sum formula, Sn equals n over 2 times open bracket a plus l close bracket, and solve for n. Now Sn represents the sum of the first n terms of an arithmetic series, n represents the number of terms that are being summed, a represents the first term of this series, and l represents the last term of this series. Now the value of Sn is given as 1,240. Now we're trying to solve for n. A represents the length of the shortest string, which is 30 centimeters, and L represents the length of the longest string, which is 50 centimeters. So substituting in those values for Sn, A and L, we can form this equation. 1,240 equals n over 2 times open bracket 30 plus 50 close bracket. Now, in the next step, actually, we can do two steps at once. We can move this division by 2 over to the other side by multiplying 1,240 by 2. We can also add 30 and 50 together since it's inside the brackets, and 30 plus 50 is 80. So the equation simplifies to 2,480 equals n times 80. So isolating n by dividing 2,480 by 80, we get n equals 2,480 divided by 80, which equals 31. Therefore, the instrument has 31 strings. Part 2. Find the difference in length between adjacent strings. Since n is known from part 1, and we found that n equals 31, which represents the number of strings this instrument has, we can use the general term of an arithmetic series formula, Tn, or the nth term, equals a plus n minus 1 in brackets times d, and we solve for d. Now a represents the first term of this series, which corresponds to the length of the shortest string, which is 30 centimeters, and d represents the common difference of this arithmetic series, which represents the difference in length between adjacent strings. Now we can use the fact that T31 is equal to 50. That's the 31st string, so that's the last string or the longest string is equal to 50 centimeters. We know that A is equal to 30. So we substitute 31 for n and then we solve for d. So the equation becomes 50 is equal to 30 plus open bracket 31 minus 1 close bracket times d. Now 31 minus 1 is 30 and we can subtract this 30 from the 50. So we can simplify the equation. We get 20 is equal to 30 times d. Dividing both sides of the equation by 30 to isolate d, we get d is equal to 20 divided by 30, which simplifies to 2 over 3. Therefore, the difference in length between adjacent strings is 2/3 of a centimeter. Question 4, Part B, Part 1. Draw the graphs of y equals the absolute value of x and y equals x plus 4 on the same set of axes. And Part 2, find the coordinates of the point of intersection of these two graphs. I've sketched the graphs of y equals x plus 4 and y equals the absolute value of x on the same set of axes drawn to scale. Now the space taken up is roughly 1/3 of an A4 page. Now the graph of y equals the absolute value of x is a V shape with the vertex at the origin and the quadrant 1 branch passing through the point 4, 4 and the quadrant 2 branch passing through -4, 4. Now the graph of y equals x plus 4 is a straight line, gradient 1, with a y-intercept of 4 and an x-intercept of -4. Now I've marked the point of intersection of the two graphs as point A. So to answer part 2, let point A be the point of intersection of the graphs of y equals the absolute value of x and y equals x plus 4. So if we go back to part 1, and from the graph we can see that the coordinates of point A are -2, 2. And I've stated that as my answer here. So from part 1, the coordinates of A are -2, 2. The question asked us to use a graphical approach to finding the coordinates of the point of intersection of the graphs of y equals the absolute value of x and y equals x plus 4. Now, as a point of interest, I'm going to find the coordinates of the point of intersection of the graphs algebraically. And we do that by solving the equation, the absolute value of x equals x plus 4. Now, this gives rise to two cases because we're dealing with an absolute value term here. We either have case 1, x plus 4 equals x, or case 2, x plus 4 equals -x. Let's consider case 1, x plus 4 equals x. If we subtract x from both sides of the equation, we get 4 equals 0, which is nonsense. So we don't have a solution for case 1. In case 2, we have x plus 4 equals -x. Combining the like terms, so moving this x here on the left-hand side over to the right-hand side, we get -2x equals 4. And I've written that here. Solving for x, we get x equals -2. Now using either y equals the absolute value of x or y equals x plus 4, substituting -2 for x, we have y equals the absolute value of -2, which equals +2, or -2 plus 4, which also equals +2. Therefore, the point of intersection has coordinates -2, 2. Question 4, Part C. Consider the function y equals 2 to the power of x. Part 1. Copy and complete the above table in your writing booklet. And Part 2. Using Simpson's rule with these 5 function values, find an estimate for the area shaded in the diagram below. For Part 1, we complete the table of values by evaluating 2 to the power of x for each value of x in the top row. When x is equal to -1, 2 to the power of -1 is 1 over 2. When x is equal to 0, 2 to the power of 0 is 1. When x is equal to 1, 2 to the power of 1 is 2. When x is equal to 2, 2 to the power of 2 is 4. And when x is equal to 3, 2 to the power of 3 is 8. To complete Part 2, we can use the extended form of Simpson's rule to do 2 applications in one go. Firstly, though, we need the value of h. Now, h is the difference between any 2 consecutive values of x. So, for example, 3 minus 2, or 2 minus 1, or 1 minus 0, and so on. The gap between successive x values is 1. That's the width of one strip. So, to use the extended form of Simpson's rule, area is approximately equal to h over 3, or 1 over 3, times open bracket, 1 over 2, that comes from this value here, plus 4 times this value, plus 2 times this value, plus 4 times this value, plus 8, which is this value here, close bracket. And that evaluates to 65 over 6, or 10 and 5 over 6 square units. Question 5, Part A. A tabletop is in the shape of a circle with a small segment removed as shown. The circle has centre O and radius 0.6 metres. The length of the straight edge AB is also 0.6 metres. Part 1. Explain why angle AOB equals pi over 3. OA equals OB, which equals 0.6 metres, and the reason is they are radii of the same circle. So if we consider triangle AOB, at this stage we can conclude that it's an isosceles triangle. Now AB, which is the base of the isosceles triangle, is equal to 0.6 metres as well, and that's given in the question. So that makes triangle AOB an equilateral triangle which has all interior angles equal to pi over 3 radians, or 60 degrees. Therefore, angle AOB equals pi over 3 as required. Part 2. Find the area of the tabletop. The area of the shaded region representing the tabletop, so that's this region here, is equal to the area of equilateral triangle AOB plus the area of major sector AOB. Note that the angle in the major sector is 5 pi over 3 radians, and we get that by subtracting the angle in the minor sector, so that's pi over 3, from 2 pi radians, since there are 2 pi radians in a full circle. Now the area of triangle AOB is found using the area rule, that's half times A times B times sine theta. In this case, A and B are the radii of the circle, which is 0.6, and theta is pi over 3. So we have half times 0.6 squared times sine of pi over 3 plus the area of the major sector AOB. Half times the radius squared times the angle in the major sector. So half times 0.6 squared times 5 pi over 3 radians. Now half times 0.6 squared is 9 over 50 and sine of pi over 3 is root 3 over 2 plus half times 0.6 squared times 5 pi over 3. So that's 9 over 50 times 5 pi over 3. So this expression here, 9 over 50 times root 3 over 2, represents the area of the triangle, plus 9 over 50 times 5 pi over 3 represents the area of the major sector. Now we can factorize out 9 over 50 from both of these terms, and we get 9 over 50 times open bracket root 3 over 2 plus 5 pi over 3 close bracket square meters in exact form, which is approximately 1.09836 square meters or 10,984 square centimeters, correct to the nearest square centimeter. Question 5, Part B. Consider the curve given by y equals 7 plus 4x cubed minus 3x to the power of 4. Part 1. Find the coordinates of the two stationary points. To find the x-coordinates of the stationary points, we first differentiate y with respect to x in the original function to find the gradient function y dash. We then solve the equation y dash equals 0 to find those x-coordinates. Once we have those x-coordinates, we substitute those values into the original function to find the corresponding y-coordinates. So differentiating y with respect to x, we get y dash equals 12x squared minus 12x cubed. Solving y dash equals 0, in other words 12x squared minus 12x cubed equals 0, we can simplify this equation by dividing all terms by 12, and we get x squared minus x cubed equals 0. Factorising out x squared from the terms on the left hand side, we get x squared times 1 minus x in brackets equals 0. And by the null factor theorem, we arrive at the solution x equals 0 or x equals 1. Now when x equals 0, using the original function, y equals 7 plus 4 times 0 cubed minus 3 times 0 to the power of 4, which equals 7. And when x equals 1, y equals 7 plus 4 times 1 cubed minus 3 times 1 to the power of 4, which equals 8. Therefore, the two stationary points have coordinates 0, 7 and 1, 8. Part 2. Find all values of x for which d squared y over dx squared equals 0. To find the second derivative d squared y over dx squared, or y double dash, we can differentiate the first derivative that we found in part 1. So from part 1, the first derivative y dash equals 12x squared minus 12x cubed. Differentiating y dash with respect to x, to get y double dash, we get 24x minus 36x squared. Solving y double dash equals 0, we get 24x minus 36x squared equals 0. We can simplify this equation by dividing all terms by 12, and we get 2x minus 3x squared equals 0. Factorising out x from the terms on the left-hand side, we get x times 2 minus 3x in brackets equals 0. And by the null factor theorem, we arrive at the solution x equals 0 or x equals 2 over 3. Part 3. Determine the nature of the stationary points. We can use the first derivative y dash to determine the nature of the stationary points, where y dash equals 12x squared minus 12x cubed. So the two stationary points are located where x equals 0 and x equals 1, and we found that in part 1. So we test around those stationary points. We draw up a table of gradients, and from those table of gradients we can determine the nature of those stationary points. So the values of x that I've chosen around x equals 0 and x equals 1 are x equals -1, x equals 1 over 2, and x equals 2. So we know that when x equals 0 and x equals 1, the value of y dash, or the value of the gradient, is 0 and 0. When x equals -1, the value of y dash is 24, so that represents a positive gradient. When x equals 1 over 2, the value of y dash is 3 over 2, and again that represents a positive gradient. And when x equals 2, the value of y dash is negative 48, which represents a negative gradient. So from the table of gradients, the stationary point at 0, 7 is a horizontal point of inflection. And we can see that from the gradients that I've drawn here under the values of y dash. So it goes up, across, and then back up again. And the stationary point at 1, 8 is a local maximum. So it goes up, across, and then down. Part 4. Sketch the curve for the domain x greater than or equal to negative 1 and less than or equal to 2. The question is asking us to sketch the graph of the function y equals 7 plus 4x cubed minus 3x to the power of 4 in the interval x greater than or equal to negative 1 and less than or equal to 2. Now we're sketching the graph of a polynomial function. Its degree is 4, so it's a quartic polynomial, and its leading coefficient is negative 3, so it'll be a concave down graph. Now when x is equal to negative 1, y is equal to 0, and when x is equal to 2, y is equal to negative 10, and they represent the endpoints of our graph. Now in previous parts we found the stationary points 0, 7 and 1, 8, and we determined their nature. The stationary point at 0, 7 is a horizontal point of inflection, and the stationary point at 1, 8 is a local maximum. So here is a sketch of the graph y equals 7 plus 4x cubed minus 3x to the power of 4. And we've shown here the horizontal point of inflection and the local maximum. And we've also shown the location of the endpoints of our graph, which is negative 1, 0 and 2, negative 10. Question 6, Part A. A glass has a shape obtained by rotating part of the parabola x equals y squared over 30 about the y-axis as shown. The glass is 10 centimeters deep. Find the volume of liquid which the glass will hold. The volume V about the y-axis is given by the formula V equals pi times the integral of x squared dy from y equals a to y equals b. Now x equals y squared over 30, but we want an equation involving x squared as the subject. So we can square both sides of this equation. So squaring the x, we get x squared, and squaring the y squared over 30, we get y to the power of 4 over 900. Now the limits of integration are from the origin, so a is equal to 0, to the point where y equals 10. So b equals 10. So our lower limit is 0, our upper limit is 10. Hence, v equals pi times the integral of y to the power of 4 over 900 dy from y equals 0 to y equals 10. Now the y to the power of 4 is being divided by 900, or being multiplied by 1 over 900, so it's a multiplying constant, and that can be taken outside of the integral to simplify the integration process. So v is equal to pi over 900 times the integral of y to the power of 4 dy from y equals 0 to y equals 10. So performing the integration, the primitive of y to the power of 4 is y to the power of 5 over 5. Now this over 5 can be taken outside as well. So we get pi over 4,500 times y to the power of 5 from y equals 0 to y equals 10. Applying the limits of integration, we get pi over 4,500 times open bracket 10 to the power of 5 minus 0 close bracket. And that evaluates to 200 pi over 9 cubic centimeters in exact form, which is approximately 69.81 cubic centimeters, correct to 2 decimal places. Question 6, Part B. The diagram shows the graphs of y equals 4 over x and y equals 5 minus x. The graphs intersect at the points A and B as shown. Part 1. Find the x coordinates of the points A and B. To find the x coordinates of the points of intersection, we solve simultaneously the equations y equals 5 minus x and y equals 4 over x. Using the substitution method, we can form this equation. 5 minus x equals 4 over x. We can eliminate the denominator x on the right hand side by multiplying all terms by the denominator x, and we get 5x minus x squared equals 4. Now we want the x squared term to be positive, and we can do that by multiplying all terms by negative 1. And we get x squared minus 5x equals negative 4. We can move the negative 4 over from the right hand side to the left hand side, so it becomes plus 4 or positive 4. And we can form this monic quadratic equation. X squared minus 5x plus 4 equals 0. Factorising the left hand side, we get x minus 1 in brackets times x minus 4 in brackets equals 0. And by the null factor theorem, we form this solution. X equals 1 or x equals 4. Therefore, the x coordinates of A and B are 1 and 4 respectively because point B is to the right of point A. Part 2. Find the area of the shaded region between y equals 4 over x and y equals 5 minus x. Between the points A and B, the line y equals 5 minus x is on or above the curve y equals 4 over x. So the area between the line and the curve is given by the integral from x equals 1 to x equals 4 of 5 minus x minus 4 over x dx. Integrating this expression, we get 5x minus x squared over 2 minus 4 times ln of x from x equals 1 to x equals 4. Applying the limits of integration, we get 5 times 4 minus 4 squared over 2 minus 4 times ln of 4 in brackets minus 5 times 1 minus 1 squared over 2 minus 4 times ln of 1 in brackets. And that simplifies to 12 minus 4 times ln of 4 in brackets minus 9 over 2 minus 0 in brackets. And that simplifies further to 15 over 2 minus 4 times ln of 4. Now as a side note, ln of 4 is equal to ln of 2 squared, which can be written as 2 times ln of 2. So the answer can be written as 15 over 2 minus 8 times ln of 2 square units. Question 6, Part C. Coal is extracted from a mine at a rate that is proportional to the amount of coal remaining in the mine. Hence the amount R remaining after T years is given by R equals R0 times e to the power of negative kt, where k is a constant and R0 is the initial amount of coal. After 20 years, 50% of the initial amount of coal remains. Part 1. Find the value of k. It is not given what the value of R0 is, which represents the initial amount of coal in the mine. Now R is equal to R0 times e to the power of negative kt. What we do know is that after 20 years, whatever the value of R0 is, 50% or half of R0 remains. So R is equal to half of R0 after 20 years. Hence we can solve for k the equation half of R0 is equal to R0 times e to the power of negative k times 20, where R0 is a positive value. In other words, it's greater than 0. So we can divide both sides of the equation by R0 to eliminate R0. So the equation simplifies to half equals e to the power of negative 20k. Taking the natural logarithm or the log base e of both sides of the equation, we get ln of 1 over 2 is equal to negative 20 times k. Now dividing both sides of the equation by negative 20, which is the coefficient of k, to isolate k, we get k is equal to ln of 1 over 2 divided by negative 20. Now ln of 1 over 2 can be written as negative ln of 2, and we're dividing that by negative 20. So a negative divided by a negative, of course, gives us a positive. So k is equal to 1 over 20 times ln of 2, which in decimal is a value that's equal to 0.03466, correct to 4 significant figures. Part 2. How many more years will elapse before only 30% of the original amount remains? Solve for t the equation 0.3 R0, which represents 30% of the original amount of coal in the mine, equal to R0 times e to the power of negative kt, where k is equal to 1 over 20 times ln of 2, which is the value of k that we found in part 1. Now, since R0 is positive, we can divide both sides of the equation by R0, similar to the process that we did in part 1, to simplify the equation, and we get 0.3 is equal to e to the power of negative kt. Taking the natural logarithm, or ln, of both sides of the equation, because we need to isolate the t, we get ln of 0.3 is equal to negative kt. Now, to isolate t, we divide ln of 0.3 by negative k. So t is equal to ln of 0.3 divided by negative k. So we get ln of 0.3 divided by, open bracket, negative 1 over 20 times ln of 2, close bracket. And that evaluates to 34.7393 and so on. Now 34.7393 minus 20 is equal to 14.7393 and so on. We'll round it at the end. So rounding this value to one decimal place, this value here represents the number of years beyond 20 years that will elapse before 30% of the original amount of coal remains. Therefore, 14.7 more years will elapse before only 30% of the original amount remains correct to one decimal place. Question 7, Part A. A factory assembles torches. Each torch requires one battery and one bulb. It is known that 6% of all batteries and 4% of all bulbs are defective. Find the probability that, in a torch selected at random, both the battery and the bulb are not defective. Give your answer in exact form. It is given that 6% of all batteries are defective. Hence, by the law of complements, 100% minus 6%, which is 94% of all batteries, are not defective. Similarly, it is given that 4% of all bulbs are defective. Hence, by the law of complements, 100% minus 4%, which is 96% of all bulbs, are not defective. Now, the probability of choosing a bulb that is either defective or not defective does not depend on whether we've chosen a battery that is either defective or not defective. So the two events are independent. So the probability of choosing a torch where both the battery and the bulb are not defective is given by 94% times 96%. Now we need to answer in exact form. So I'm going to convert these percentages into simplified fractions. So we have 47 over 50 times 24 over 25, which gives us 564 over 625. To help visualize the problem, we can draw a two-stage probability tree diagram that models this situation. In the first stage, we're choosing a battery, and in the second stage, we're choosing a bulb. Now the D represents defective and D bar represents not defective. Now on each of the branches, we write the corresponding percentages. So for a defective battery, it's 6%. For a battery that's not defective, it's 94%. And whichever battery we choose, whether it's defective or not defective, it's a 4% chance of choosing a defective bulb and a 96% chance of choosing a bulb that is not defective. Now the outcome that we're interested in is choosing a battery and a bulb that are both not defective. So we're following this path here, these two branches. So this branch here and this branch here. and that's why I've labelled it with an asterisk. So 94% times 96% in exact form gives us 564 over 625. Question 7, Part B. ABCD is a parallelogram. The point X lies on CD, the point Y lies on AB, and AX equals CY equals BC as shown in the diagram. Part 1. Copy the diagram into your writing booklet, and Part 2. Explain why angle ADX equals angle CBY. Part 1 asks us to copy the diagram into our writing booklets. So here is parallelogram ABCD with all the markings that are shown in the original diagram. Now for Part 2, we're asked for a reason why angle ADX equals angle CBY. Now here's angle ADX, here's angle CBY, and they are opposite angles in a parallelogram, and opposite angles in a parallelogram are equal. And I've written the reason here. Opposite angles in parallelogram ABCD, so I'm specific as to which parallelogram I'm referring to, are equal. Part 3. Show that AD equals AX. In a parallelogram, opposite sides are equal in length. So in parallelogram ABCD, side AD is equal to side BC, and I've marked that with the dashes shown. And I've also stated that here in Part 3 as part of the reasoning. So AD equals BC, and opposite sides of parallelogram ABCD are equal. Now AX equals BC, and that's given in the original question, and that was already marked in the diagram. So AX has a dash, and BC has the same dash. And because AD equals BC and AX equals BC, hence AD equals AX. Part 4. Show that triangles ADX and CBY are congruent. Angle AXD equals angle ADX, which equals angle CBY, which equals angle BYC. And the reason is base angles of isosceles triangles ADX and CBY. Also, angle DAX is equal to angle BCY, and the reason is angle sum of isosceles triangles with identical base angles. Now AD equals AX, which equals CY, which equals BC, and that was proven previously. Hence, triangle ADX is congruent to triangle CBY, and the test is side angle side, or SAS. And I've shown the reasoning here. I'll just go through it one more time. Angle AXD equals angle ADX, which equals angle CBY, which equals angle BYC, and the reason is base angles of isosceles triangles ADX and CBY. Angle DAX equals angle BCY. The reason is angle sum of isosceles triangles with identical base angles. AD equals AX, which equals CY, which equals BC, and that was proven previously. Hence, triangle ADX is congruent to triangle CBY, and the reason is side angle side, or SAS. Part 5. Hence prove that AYCX is a parallelogram. Firstly, BY equals DX, and that's because they are corresponding sides of congruent triangles ADX and CBY, which was proven previously. Next, AB equals DC, and that's because they are opposite sides of parallelogram ABCD. Hence, AB minus BY, which is equal to AY, is equal to DC minus DX, which is equal to XC. So that implies again that AY equals XC, and I've marked those two sides appropriately with the triple dashes. Now AX is equal to YC, and that was given in the original question. So we have a quadrilateral AYCX with opposite sides equal, which makes AYCX a parallelogram. And here is the proof written down. and I'll go through it quickly one more time. by equals dx, corresponding sides of congruent triangles ADX and CBY, which was proven previously. AB equals DC. The reason is opposite sides of parallelogram ABCD, of course, are equal. Hence, AB minus BY is equal to DC minus DX, which implies that AY is equal to XC. Now, AX is equal to YC, which is given. Therefore, AYCX is a parallelogram, and the reason is opposite sides are equal. Question 7, Part C. The graph shows the levels of a pollutant in the atmosphere over the past 50 years. Describe briefly how the level of this pollutant has changed over this period of time. Include mention of the rate of change. At any point along the curve, the gradient of the tangent is positive, hence the level of pollution is increasing over time. However, the gradient of the tangent to the curve just after 1945 is greater than the gradient of the tangent to the curve just before 1995, which means the level of pollution is increasing but at a decreasing rate over time. So from 1945 to 1995, we can say that the first derivative, dy dx, is greater than 0 or positive, and the second derivative, d squared y over dx squared, is less than 0 or negative. Question 7, Part D, Part 1. Given that log base A of B equals 2.75 and log base A of C equals 0.25, find the value of log base A of B over C. Using the subtraction logarithm law, log base A of B over C is equal to log base A of B minus log base A of C. Now log base A of B is 2.75, log base A of C is 0.25, so 2.75 minus 0.25 is equal to 2.5. Part 2. Find the value of log base A of BC in brackets to the power of 2. Using the product logarithm law, log base A of BC in brackets to the power of 2 is 2 times log base A of BC. Now using the addition logarithm law, log base A of BC is log base A of B plus log base A of C. So combining both of those logarithm laws, the product logarithm law and the addition logarithm law, we have 2 times open bracket log base A of B plus log base A of C close bracket. Now log base A of B is 2.75, log base A of C is 0.25. 2.75 plus 0.25 is equal to 3. Multiplying that by 2, we get 6. Question 8, Part A. Greg and Jack are playing in a golf tournament. They will play 2 rounds and each has an equal chance of winning the first round. If Greg wins the first round, his probability of winning the second round is increased to 0.6. If Greg loses the first round, his probability of winning the second round is reduced to 0.3. Part 1. Draw a tree diagram for the 2-round sequence. Label each branch of the diagram with the appropriate probability. I've drawn a 2-stage probability tree diagram where the first stage represents the result of playing the first round of the game and the second stage represents the result of playing the second round of the game. Now in the first round of the game, it is given that there's an equal chance of either Greg or Jack winning. So the probabilities on each of the branches are 0.5 and 0.5. Notice that the sum of the probabilities in each stage must equal 1. Now, if Greg wins the first round, the probability that Greg wins the second round is increased to 0.6. by the law of complements, that means that the probability of Jack winning the second round if Greg was to win the first round is reduced to 0.4. Again, 0.6 plus 0.4 equals 1, and the sum of the probabilities must equal 1. Now, if Jack was to win the first round, the probability that Greg wins the second round is reduced to 0.3. Again, by the law of complements, the probability that Jack wins the second round is increased to 0.7. Part 2. Find the probability that Greg wins exactly one round. Looking at the tree diagram that we drew in Part 1, out of the 4 outcomes, there are 2 outcomes that show Greg winning exactly one round. Either Greg wins the first round and then Jack wins the second round, or Jack wins the first round and then Greg wins the second round. And I've marked those 2 outcomes with an asterisk. Now, looking at the solution, the probability that Greg wins exactly one game is equal to the probability that Greg wins the first round and then Jack wins the second round, plus the probability that Jack wins the first round and then Greg wins the second round. So multiplying along the relevant branches of the tree diagram, we have 0.5 times 0.4 plus 0.5 times 0.3, and that equals 0.35 or 35%. Question 8, Part B. On 1 July 1985, Anna invested $10,000 in a bank account that paid interest at a fixed rate of 8% per annum compounded annually. Part 1. How much would be in the account after the payment of interest on 1 July 1995 if no additional deposits were made? The question is asking for the amount in the account or the future value of the account 10 years after the deposit is made. Now, the deposit is made on 1 July 1985, and we want to find out the amount in the account on 1 July 1995, and that's where we get the 10 years from. So using the compound interest or future value formula, that is, the future value FV is equal to the present value PV times 1 plus R in brackets to the power of n, where PV represents the principal or the amount invested, which is $10,000. R represents the compound interest rate per period. In this case, it's 8% per annum. And N represents the total number of compounding periods. Now, it's compounded annually over 10 years, so N is equal to 10. So the future value, or the amount in the account after 10 years, is equal to 10,000 times 1 plus 8%, or 1.08 as a decimal, to the power of 10, which evaluates to 21,589.24997 and so on. But we need to round that to 2 decimal places because it represents a money amount. So therefore, $21,589.25 will be in the account on 1 July 1995. Part 2. In fact, Anna added $1,000 to her account on 1 July each year, beginning on 1 July 1986. How much was in her account on 1 July 1995 after the payment of interest and her deposit? We can model the annuity as a geometric progression or a geometric series. Now we can think about it this way. The first deposit of $1,000 will be in the account for a total of 9 years. So from 1 July 1986 to 1 July 1995. So its future value is given by 1,000 times 1.08 to the power of 9. So that's 1 plus R, so R is 8%, to the power of 9. Now the following year, the next deposit of $1,000 will be in the account for 1 year less. It'll only be in the account for 8 years. So its future value is 1,000 times 1.08 to the power of 8. And the pattern continues. Now on the second last year, so that's 1 July 1994, This deposit of $1,000 will be in the account for 1 year, so its future value is 1,000 times 1.08 to the power of 1. And the final deposit of $1,000 is going to be made on 1 July 1995, but then it's going to be withdrawn immediately. So it'll earn no interest. So its future value is 1,000 times 1.08 to the power of 0. And 1.08 to the power of 0, of course, is 1. Now we can factorize out 1,000 from all of these terms. And we get 1,000 times, open bracket, 1 plus 1.08 plus 1.08 squared plus plus 1.08 to the power of 9, close bracket. Now if we look at what's in the brackets here, we have 10 terms of a geometric series, where the first term is 1 and the common ratio is 1.08. So we can model what's in the brackets using the sum of a geometric series formula. So it's going to be 1 minus r to the power of 10, so 1 minus 1.08 to the power of 10 over 1 minus 1.08. And this fraction's being multiplied by 1,000. And that evaluates to 14,486.56, or $14,486.56. But the question is asking for the total amount in the account, including the initial deposit of $10,000 that we found in part 1. So the amount in the account is 14,486.56 plus 21,589.25 from part 1, which equals $36,075.81. Part 3. Anna's friend, Jennifer, invested $10,000 in an account at another bank on 1 July 1985 and made no further deposits. On 1 July 1995, the balance of Jennifer's account was $35,478. What was the annual rate of compound interest paid on Jennifer's account? Using the future value formula, that is, future value is equal to the present value times 1 plus r in brackets to the power of n, we want to solve this equation for r, knowing the future value, the present value, and n. So substituting those values for FV, PV, and n, we have 35,478 is equal to 10,000 times 1 plus r in brackets to the power of 10. Dividing both sides of the equation by 10,000, we get 3.5478 is equal to 1 plus r in brackets to the power of 10. Taking the 10th root of both sides of the equation, we get the 10th root of 3.5478 is equal to 1 plus r. And finally, to isolate r, we subtract 1 from the 10th root of 3.5478, and we get r is equal to 0.135001344, and so on. Therefore, the interest rate is 13.5% as a percentage per annum, correct to 1 decimal place. Question 9, Part A. A rectangular beam of width W centimeters and depth D centimeters is cut from a cylindrical pine log as shown. The diameter of the cross-section of the log, and hence the diagonal of the cross-section of the beam, is 15 centimeters. The strength, S, of the beam is proportional to the product of its width and the square of its depth, so that S equals K times D squared times W. Part 1. Show that S equals K times, open bracket, 225W minus W cubed, close bracket. It is given that S is equal to K D squared W, and we're asked to show that S is equal to K times, open bracket, 225W minus W cubed, close bracket. Which means we need to express D in terms of W. So if we go back to the diagram, we have a right angled triangle there at the end of the log. We have the width W and the depth D, and we have the hypotenuse of the triangle, 15 centimeters. So using Pythagoras' theorem, we can express D in terms of W. D squared is equal to 15 squared minus W squared. Now 15 squared is 225, so D squared is equal to 225 minus W squared. Now if we go back to this formula here, we replace or substitute the D squared out, and in its place we substitute 225 minus W squared. So S equals KD squared W, written in terms of W, is K times open bracket 225 minus W squared close bracket times W. Now multiplying through by W, we get S is equal to K times open bracket 225W minus W cubed close bracket as required. Part 2. What numerical dimensions will give a beam of maximum strength? Justify your answer. The question is asking us to maximize S, which implies the use of differential calculus. Now S is equal to K times open bracket 225W minus W cubed close bracket. Differentiating S with respect to W to find an expression for the first derivative S dash, we get S dash is equal to K times open bracket 225 minus 3W squared close bracket. Next, we solve for W the equation S dash equals 0. Now whatever values of W that we find, we need to test those values of W that they correspond to a maximum value of S, not a minimum value of S or a horizontal point of inflection. And we can use the second derivative for that later on. So firstly, to solve S dash equals 0. So we have K times open bracket 225 minus 3W squared close bracket equals 0, where K is a positive value. Now because K is not 0, we can divide both sides of the equation by K to eliminate K, which simplifies the equation somewhat. And we get 225 minus 3W squared equals 0. Isolating 3W squared, we get 3W squared is equal to 225. Now we can isolate W squared by dividing both sides of the equation by 3, and we get W squared is equal to 75. And taking the positive square root of both sides, since W represents a length or a width, we get W is equal to the square root of 75, or 5 root 3 centimeters in simple surd form. Now to find the second derivative, S double dash, we differentiate the first derivative with respect to W, and we get negative 6 times K times W. Now when W is equal to 5 root 3, S double dash is equal to negative 30 times K times root 3. Now K is positive, so a negative number times a positive gives us a negative. So because S double dash is negative, S is maximized when W is equal to 5 root 3 centimeters. Now given that D squared is equal to 225 minus W squared from part 1, because at this point, now that we have W, we need to find the depth D that corresponds to the value of W that we've found. When W is equal to 5 root 3 centimeters, D squared is equal to 225 minus 5 root 3 in brackets squared, which equals to 150. Taking the positive square root of both sides to isolate D, we get D is equal to root 150, or 5 root 6 centimeters in simple surd form. Therefore, the strength of the beam is maximum when the width W is equal to 5 root 3 centimeters and the depth D is equal to 5 root 6 centimeters. Part 3. A square beam with diagonal 15 centimeters could have been cut from the log. Show that the rectangular beam of maximum strength is more than 8% stronger than this square beam. For a square beam, the depth D is equal to the width W. Hence from part 1, if you recall the equation D squared is equal to 225 minus W squared, we substitute W for D and we form this equation. W squared is equal to 225 minus w squared. Now we can move this negative w squared over to the left-hand side and we get 2w squared is equal to 225. Dividing both sides of the equation by 2 to isolate w squared, and we get w squared is equal to 225 over 2. And taking the positive square root of both sides, we get w is equal to 15 over the square root of 2. Now from part 1, recall that the strength S in terms of w is k times, open bracket, 225w minus w cubed, close bracket. Now for a rectangular beam of maximum strength, when w is equal to 5 root 3, which we found in part 2, S is equal to k times, open bracket, 225 times 5 root 3 minus 5 root 3 in brackets cubed, close bracket. And we'll call this equation number 1. Now for a square beam, W is equal to 15 over root 2. So the strength S is equal to K times, open bracket, 225 times 15 over root 2 minus 15 over root 2 in brackets cubed, close bracket, and we'll call this equation number 2. Now dividing equation number 2 by equation number 1, even though it involves K, the K's end up cancelling out and we end up with this value, 1.08866 and so on. Multiplying this value by 100 to convert it into a percentage, we get 108.866 and so on percent. Now this implies that the rectangular beam of maximum strength is more than 8% stronger than the square beam as required. Question 9, Part B. A particle is observed as it moves in a straight line in the period between t equals 0 and t equals 10. Its velocity v at time t is shown on the graph above. Copy or trace this graph into your writing booklet. Part 1. On the time axis, mark and clearly label with the letter Z the times when the acceleration of the particle is 0. An acceleration of 0 implies dv dt, or the rate of change of velocity with respect to time, equals 0. And that corresponds to the two stationary points on the velocity time curve here and here. Now I've labelled the points in time where those stationary points occur with the letter Z, directly underneath this stationary point here and directly above this stationary point here. Part 2. On the time axis, mark and clearly label with the letter G the time when the acceleration is greatest. The point on the velocity versus time curve where acceleration is at a maximum, that is, the rate of change of velocity with respect to time is at a maximum, is the point where the gradient to the tangent to the curve is at a maximum. And that occurs roughly at this point here. And I've labelled it on the curve with A max. Now the point in time where that occurs has been labelled on the time axis with the letter G directly underneath A max. Part 3. There are 3 occasions when the particle is at rest. That is, t equals 0, t equals 7 and t equals 10. The particle is furthest from its initial position on one of these occasions. Indicate which occasion, giving reasons for your answer. In order to answer part 3, we need to consider the signed area bounded by the curve and the time axis. So the area here is positive and the area here is negative. Now, since the curve from t equals 0 to t equals 7 is on or above the time axis, that means the particle is moving to the right, starting at the origin O between t equals 0 and t equals 7. In other words, from here to here. After t equals 7, because the area here is negative, this means that the particle has changed direction and is moving back toward the origin. But it's clear from the graph that the area from t equals 0 to t equals 7, the magnitude of the area specifically, is greater than the magnitude of the area from t equals 7 to t equals 10. So we have a large positive area here, a small negative area here. So what's actually happening is that the particle has moved to the furthest extent to the right, away from the origin, at time t equals 7. After time t equals 7, the particle has moved back toward the origin some distance, but not quite reaching the origin, of course. So here is the explanation. We'll go through this. So the particle is moving to the right, starting at O, between t equals 0 and t equals 7. Now from t equals 7 to t equals 10, the particle changes direction and moves back toward, but not reaching, the origin. Now by observation, the signed area bounded by the curve and the time axis, which represents the displacement of the particle, is maximum between t equals 0 and t equals 7. Therefore, the particle is furthest from the origin at time t equals 7. Question 10, Part A, Part 1. Draw the graphs of y equals 4 cos x and y equals 2 minus x on the same set of axes for x greater than or equal to negative 2 pi and less than or equal to 2 pi. Here is a sketch of the graphs of y equals 4 cos x, and it has a range from negative 4 to positive 4. So it's the graph of y equals cos x that has been dilated vertically by a factor of 4. Now on the same set of axes, I've sketched the graph of y equals 2 minus x. So it has a gradient of negative 1, a y-intercept of 2, and an x-intercept of 2. Now these graphs have been drawn to scale as best as possible. Make sure we draw the axes using a ruler, marking the origin, the x-axis, and the y-axis. Part 2. Explain why all the solutions of the equation 4 cos x equals 2 minus x must lie between x equals negative 2 and x equals 6. The graphs of y equals 4 cos x and y equals 2 minus x are continuous. That means there are no breaks or discontinuities. And both have a range of y greater than or equal to negative 4 and less than or equal to 4 in the interval x greater than or equal to negative 2 and less than or equal to 6. Now I've marked the interval here. Here's x equals negative 2 and x equals 6. So looking inside this interval, the graph of y equals 4 cos x has a maximum value of 4 and a minimum value of negative 4. And the graph of y equals 2 minus x has a maximum value of 4 here and a maximum value of negative 4 here. So outside the interval, the range of y equals 2 minus x extends beyond y equals 4. So if we go below x equals negative 2, we can see that the line goes above y equals 4. And if we go beyond x equals 6, y equals 2 minus x goes below y equals negative 4. But the cosine curve will only go from negative 4 to positive 4. Hence, all solutions to 4 cos x equals 2 minus x must lie in the interval x greater than or equal to negative 2 and less than or equal to 6. And they're evident in the points of intersection of the two graphs, here and here. Now I'll put the text of the explanation on screen here for your reference. And I'll just go through it one more time. The graphs of y equals 4 cos x and y equals 2 minus x are continuous and both have a range y greater than or equal to negative 4 and less than or equal to 4 in the interval x greater than or equal to negative 2 and less than or equal to 6. Outside the interval, the range of y equals 2 minus x extends beyond y equals 4 or below y equals negative 4. Hence, all solutions to 4 cos x equals 2 minus x must lie in the interval x greater than or equal to negative 2 and less than or equal to 6. Question 10, Part B. Two particles A and B start moving on the x-axis at time t equals 0. The position of particle A at time t is given by x equals -6 plus 2t minus half t squared, and the position of particle B at time t is given by x equals 4 times sine t. Part 1. Find expressions for the velocities of the two particles. To find the velocity of particle A, we differentiate the displacement equation of particle A, and the displacement equation is x equals -6 plus 2t minus half t squared. So to find the velocity, we find dx dt, so differentiating x with respect to t, we get 2 minus t. Now to find the velocity of particle B, we differentiate its displacement equation. So the displacement equation of particle B is x equals 4 times sine t. Differentiating x with respect to t, we get v equals dx dt, which equals 4 times cos t. Part 2. Use Part A to show that there are exactly two occasions, t1 and t2, when these two particles have the same velocity. Using the graphs drawn in Part A, the graphs represent the velocities of particles A and B. Now recall from Part 1, we found the velocity of particle A, which is v equals 2 minus t. The velocity of particle B was v equals 4 cos t. Now if we sketched v equals 2 minus t and v equals 4 cos t on the same set of axes, we would obtain exactly the same graph that we sketched in Part A. Now the graphs that we sketched in Part A, the x-axis, well, is the x-coordinate, the y-axis of course is the y-coordinate, but if we represent velocity versus time, the y-coordinate becomes velocity and the x-coordinate becomes time. But we would obtain exactly the same two graphs, and the points of intersection represent the points where the velocities of both particles are the same. And I've labeled them here. So there's one here and one here. We discount this point of intersection because we're only interested in values of time greater than or equal to 0. In other words, quadrants 1 and 4. So going back to our explanation, the points of intersection of the graphs represent the times where the velocities are the same for time t greater than or equal to 0. And by inspection of the graphs, the value of t1 is between 0 and 2, and the value of t2 is between 2 and 6. Part 3. Show that the distance travelled by particle A between these two occasions is 4 minus 2 times open bracket t1 plus t2 close bracket plus half times open bracket t1 squared plus t2 squared close bracket. For values of time between t1 and 2, where t1 is less than 2, the particle is moving to the right. Hence, the distance travelled is given by x of 2 minus x of t1. We'll call this expression number 1. Now, after time t equals 2, that is, values of time between 2 and t2, the particle moves to the left. So at time t equals 2, the particle changes direction. Hence, the distance travelled is given by x of 2 minus x of t2, and we call this expression number 2. Now, it's important to note that at time t equals 2, the particle changes direction, and this needs to be taken into account when finding the total distance travelled. So to find the total distance travelled, we add both of these expressions together. So expression number 1 and expression number 2. Now we have two of these x of 2's, and so we get 2 times x of 2, and we can factorise out the negative from minus x of t1 and minus x of t2. So the total distance travelled is given by 2 times x of 2 minus open bracket x of t1 plus x of t2 close bracket. Now recall the displacement equation for particle A, which was x equals -6 plus 2t minus half t squared. So substituting t equals 2, t equals t1 and t equals t2 in the relevant spots, we get 2 times open bracket -6 plus 2 times 2 minus half times 2 squared close bracket, so that's 2 times x of 2, minus, now open square bracket, open bracket, minus 6 plus 2 times t1 minus half times t1 squared, close bracket, plus, open bracket, minus 6 plus 2 times t2 minus half times t2 squared, close bracket, close square bracket. So we can simplify the numerical component. 2 times x of 2 is negative 8. And we have negative 6 minus 6, which gives us negative 12. So that's inside the square brackets here and here. And we have plus 2 times t1 plus t2 in brackets, so factorising out the 2, minus half times t1 squared plus t2 squared, so factorising out negative half. Now expanding the square brackets, we have negative 8 minus negative 12, so negative 8 plus 12, we get positive 4. Now we have a minus here and a plus here, so we get minus 2 times t1 plus t2 in brackets. Now we have a minus here and a minus here, so we get plus half times t1 squared plus t2 squared in brackets as required. Part 4. Show that the two particles never meet. The displacement curve for particle A, x equals negative 6 plus 2t minus half t squared, is a concave down parabola with the vertex at t equals 2. If you recall, at t equals 2, that's when particle A changes direction. Now at t equals 2, the displacement is negative 4. Hence, the displacement range of particle A is x less than or equal to negative 4, with x equaling negative 4 occurring only once at time t equals 2. Now, the displacement curve for particle B, x equals 4 times sine t, has a displacement range of x greater than or equal to negative 4 and less than or equal to 4. So the only time where particle A and particle B could meet would only occur at time t equals 2, no other time. Now at time t equals 2, the displacement of particle B is given by x of 2, which equals 4 times sine 2, which equals 3.637 and so on, which is not equal to negative 4. Therefore, the two particles never meet.